All right, so we're talking about 9.2, absolute entropy and entropy change. This is ultimately going to be about quantifying entropy. But before we get into that, a little warm-up question. So pause the video, read this, and think about it for a moment. Okay, hopefully you pause the video and have thought about this. So we add a cube of ice to hot water. It's sealed, and there's no heat exchange with the surroundings. So this is more of a Unit 6 thermo question. What happened to the total entropy of the system when it reaches equilibrium? So when the temperatures equalize. And what happened to the total entropy of the system? Well, hopefully you realize if there's no heat exchange with the surroundings, then the total energy did not change, right? All of our ice presumably melted, but maybe some of it stayed ice. All of that energy is trapped in the container, right? There's no heat traveling out. But what happened? Well, if it's really hot water to entropy, entropy probably increased because some of that ice melted. And when ice turns into liquid water, well, that's a more, disordered state. Now I realize this doesn't give any quantities. You might say, well, was it a giant, 10-gallon brick of ice and a tiny cup of hot water? Let's assume it was enough that the ice melted. We would definitely have some total entropy increasing in the system. So as I said, we've been talking about entropy qualitatively. We can quantify it. And what we will be seeing with this is, again, that entropy of the universe wants to increase. Now, this is technically called the second law of thermodynamics, that it increases for spontaneous processes and remains unchanged when a system is at equilibrium. So let's just focus on the fact that entropy is going to increase typically if something is spontaneous, and we'll talk more about that terms. I think in our next topic in more depth. For now, just think about spontaneous means something occurs, not necessarily that it occurs quickly. So when something is favored by the universe, it's something where the entropy of the universe increases, meaning that if I add the change in entropy of the system to the change in entropy of its surroundings, that value is greater than 0. However, when something is at equilibrium, we would say the entropy of the universe isn't changing, right? These things are just going back and forth in equal rates, so I don't have a net change in how many products and how many reactants I have. Now, when we talk about entropy of the universe and the system and the surroundings, this is getting very out there. What we're really talking about in the rest of this unit is going to be the system, right? What's in my beaker? What reaction am I looking at? And so that's why we'll be using this notation, delta S reaction. Again, that little circle meaning at standard conditions, to talk about the entropy of just, what is the process in front of my face. Now, how do we quantitatively talk about delta S of the system or the reaction, whatever? It's the same way we do this with finding delta H of reaction using heats of formation, just like we did in Unit 6. So the overall delta S for reaction, we'll take the sum of the delta S's of formation for the products and subtract the sum of the delta S of formation for the reactants. Now, when we do that, we always want to make sure we're multiplying by the coefficients as necessary for each of these substances, okay? So what do we mean when we say the entropy of a substance, right? So it's sort of like what we talked about before, how, something like NO2 has less entropy than N2O4, right? Something that has just by itself, just looking at the molecule, more ways for it to be organized is going to be a higher entropy substance, right? So we can actually quantify these things, and you don't have to calculate them. They're just going to be given to you in a table form, as you'll see on the next slide. We can use these when we look at, okay, now I have an overall reaction. Can I plug in these individual molar entropies or entropies of formation for individual substances to find what is the net change in entropy of this system? Now, one weird thing, and I do want to emphasize this because we don't talk about unit conversions too much in this class. Delta H's, so changes in enthalpy, whether it's formation or for the reaction, are going to be in kilojoules per mole 99% of the time. However, delta S values always come in joules per mole Kelvin. So joules on top, moles and Kelvin on the bottom. you will have to be converting between joules and kilojoules. Generally speaking, I would say convert the entropies into kilojoules. And that is generally just going to be dividing by 1,000 to turn it into kilojoules. Okay. Now, you might be wondering, what does the per Kelvin mean? It means the effective entropy in a system, talking about its total thermodynamic favorability, which again we'll get to, is dependent on temperature a little bit, right? So if I have higher temperature, I'm going to have something more disordered. If I have lower temperature, it's going to be more ordered, despite whatever the individual entropy of that molecule may or may not be, right? Temperature is going to play a role. So that's why we have this per Kelvin put into entropy. So I've just got a table here. You do not have to memorize these. Again, values for entropy, just like heats of formation, will be given to you in a given problem. But we need to be familiar with seeing the ranges. And here's 3 different sets. Can you notice any patterns? Just pause the video. Take 15 seconds. You notice any patterns here? Hopefully one you see is that my gases, very high entropy. My liquids, sort of in the same range, but my solids definitely much lower in entropy than something like, helium. We also see things like diamond, which is a very organized chemical. If you look at its structure, very rigid network covalent compared to something like pure sodium, right? It's still a solid, so it's fairly low in entropy compared to like a gas like xenon, but sodium is definitely more disorganized than diamond, for example. So not something we're really going to be comparing too much, just substance to substance based on states of matter, but I thought it was a worthwhile thing to note there. So again, let's get to that entropy of reaction calculation. Again, what this looks like is summing the entropies of the products minus the sum of the reactants, and pay attention to your coefficients, which need to get multiplied by the individual molar entropies. So here are my 2 products, delta S of D, and they're being multiplied by those coefficients. We sum those, we subtract the same thing for my reactants, multiplied by their respective coefficients. So I've just got one quick example here, and it's actually one where you see something worked, and we're going to analyze how they did. So here is the reaction that we're looking at. 2PCl3 plus O2 turns into 2POCl3. And we are given the entropies for each substance right here. So we've got one product, right? If I want to calculate delta S, I'm not even going to look at these students' work first. I'm just going to write it out here. So delta S of the reaction is going to be the sum of my products. Whoa, that was a terrible sigma. Sum of my products minus the sum of my reactants. Dear God, I'm really losing it, guys. So my products, I've just got the one POCl3, but there's 2 of them. So I'm going to do 2 times whatever the entropy is for that substance, which is 325.45. And I know all of these are in joules per mole Kelvin, so I'm not going to bother writing the units like these dumbo students did. That's my only product, right? So then I move to my reactants. So first I've got the PCl3, which I also have 2 of. So it's going to be 2 times PCl3, which is 311.78, plus the value of O2, which is just 1, and 205.14, right? So let's look back at what our friends did. It looks like student B switched up the order, right? They did reactants minus products. Reactants minus products. Student A looks like they forgot the coefficients, right? They just went straight to the thing. They didn't include the times 2. So we did it right below. And what you should get, this is really fun. You're going to watch me punch stuff in on my calculator. 2 times 3.78. Should get negative 117, there's 177.8, and we'll slap those units on now, joule per mole Kelvin. Okay, so looking at this, a negative delta S, does that mean the system increased or decreased in entropy? Well, entropy went down, so entropy decreased. And does this track with what we see in the chemical equation? Could you look at this chemical equation without any numbers and say, yeah, entropy definitely decreased? You sure could, because what happened? I have 3 moles of gas on the left, and I end up with 2 moles of gas on the right. Now, you could also make the case, again, that this is a more complex molecule, the POCl3, than either of these two, but overall having more or less particles is going to have more of an impact on entropy than something like sheer molecule complexity. So that's 9.2. Again, pretty straightforward. Next topics are really going to crunch it up, so get ready for that. But good luck with the homework, and I miss you guys dearly.